Okay, let's say that you have the oligo analyzer opened up. Then what you're going to do is you're going to enter your primer sequence. For example, let's say that was the sequence of my first primer. Just highlight it and then copy it. Copy it, and then you're going to open up that oligo analyzer sequence, the website, and enter your sequence by pasting it there. Okay, so pasted that. So you don't have to enter this 5' N symbol there. You just need to enter the DNA sequence only, and 3' N should be removed as well. Okay, that's the sequence of your primer. Let's say that is what you like. Okay, and then you're gonna analyze the sequence by clicking on the analyze of key, function key there. Let's see what happens. Okay. Yeah, so it was okay. Let's already finished the analysis, right? The analysis result is shown up at the bottom of it. So the sequence of your primer, I just entered. Okay, so that sequence is showing up there. Okay, and its complementary sequence will be that. Okay, so it's going to bind that sequence. And the length of it is only 20 nucleotide long. GC content is about 45%. Based on that, the melting temperature, there are different methods you can use to calculate the melting temperature. My calculation was about 53. Yeah, it says about 52.7 degrees in Celsius. Yeah, about the same, right? Molecular weight, that's fine. Extinct coefficient, you don't have to know about that. For your PCR condition, that's fine. Or other information, and then other important analysis you can do. So the most important part is the melting temperature. They will calculate that for you. And then here, more options there. Hairpin structure, possible hairpin structure that can form within this primer sequence. If you click on it, it's going to show you what those are. There you go. So yeah, so this one, image of the sequence. So these are the possible hairpin structure that it can form. Let's take a look at it. Click on it. Yes, it's pretty weak between, so that's the 5' N, 3' N. On that side, there's a G and C match, A and T match. So there's that hairpin that can form, which is pretty weak. It's made of only 2 nucleotides, so it's not too bad. You can just ignore that. That's fine. The first one, and then there was the second one. Yes. Oh, so there's one more nucleotide that can add, and that's fine. That's weak again. So at the higher temperature, like 53 degrees, it's going to break up. So see delta G. At the lower temperature, they may be formed, but if you use higher unknown temperature, they will go away. And what is this? So another hairpin possibility, but all of them are not that bad. Okay, so that's fine. You can maybe copy and paste this, okay, and include it in your analysis. So that's the hairpin structure. And how about self-dimer? Can these primers bind together? So you can click on that. So there you go. These are all possible self-dimers between the 2 primers with the same sequences. Can they form these dimers? So these are self-dimers. Okay, so 3 matches, maybe GC and TT and AAs. That's possible dimers. Another match there. Another match there. So these are all possible dimer formations here, there. Okay, it's showing all possible dimer formation, but I don't see any really significant dimer formation because they are only made up with 2 nucleotides. They will be all easily broken up. So these are just this much energy. If we are giving them through various treatment like a thermal energy, they will break up. So those are not significant challenges that you face, but that's fine. I just want you to know how you can do these analysis. Okay, those are the self-dimer analysis. How about the heterodimer? What does that mean? Would this primer bind with the second primer that you will develop? That's what heterodimer is. Let's see what happens if you click on it. So yeah, yes, you have the first primer sequence entered. What's the sequence of the second primer? It's asking you to enter that. So I'm going to enter the sequence of my second primer, which I typed up here, right? It's the 5' and 3' N, but it's kind of an opposite sequence. So I'm going to copy and paste that on here. But it should be flipped. So Actually, the sequence is not correct. Is that right? It should be TTAGTC instead of AAT. So that is the 5' end. So we need to flip that somehow. Let's see, how do I make that? You can maybe type it up again, maybe. Instead of doing that, enter it as opposite way. TTA, GTC, TTA, GTC, CTT, and TGG, CAA, and TCT, TA is the sequence. I just typed up that sequence based on this sequence you can get from the opposite side, TTA, GTC. See, that's what I typed up, so you can get rid of that. Okay, so now that's the correct sequence on the correct orientation, right? So now we're going to look if these two primers can bind together. So those are the heterodimers. Let's see if you click on that. So yeah, so that's the analysis. There are some possible binding. Yeah, there are some. There are triple nucleotide binding, but since it's mostly made of T's and A's, it's just not strong. Okay, double, 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 but not that significant. You know, the bad things may have like multiple nucleotides matched up, but these two heterodimers are not that bad. Okay, so that's how you do the analysis. Okay. So I want you to do all these analysis and then, you know, copy and paste your result on a Word file. Okay, and then so you can tell me what melting temperature of each primer is, and what is the possible hairpin that structures each primer has, and what is the possible self-dimer each primer has, and then between those two primers, what are the possible heterodimers, you know, you can form. Okay, so you have to do the analysis of each primer thoroughly and copy and paste those all in your Word file, and then at the end you will do the heterodimer analysis between those two primers. Okay, so that's the assignments you need to do. Okay, once you did that, and then so you will do the analysis. So the answers for all these should be included in your analysis. Primer sequence, of course, size of your primer, and then expected size between the two primers, okay, and the melting temperature, and then underlying temperature and everything. Secondary structure, hairpin, primer dimer, and then heterodimer should be included, okay. And at the end, on top of that, you have to come up with the PCR condition that you will use when you do your PCR using those two primers, okay. Again, the denaturation is pretty generic, you know, 95 degrees for 1 minute. Okay, underlying temperature is the thing that you're going to come up with. Okay, between the two primers, underlying temperature. Let's say the first primer was 53 degrees. That's what the analysis did. And what is the underlying temperature of the second one? We haven't done that, but you will do that, and you will know what the recommended underlying temperature is. And let's say that was like 48 degrees, right? Then which temperature you're going to use for annealing? The answer is, of course, the lower temperature. If we use a higher temperature, the other primer would not bind, right? So you have to use the lower underlying temperature between the two underlying temperature of the primers, okay? And the time is about 1 minute. And the extension is about 74 degrees, about 1 minute. So you have to come up with that PCR condition, okay? Once you do that, you have to upload your document in your course shelf. That's the end of this lab, okay?